Hi, so in the last two videos, we learned what is E, how does it come about, and how to calculate E with great precision using Maclaurin time series. Maclaurin series. Now, let's use this E because definitely it's a preferred base for both exponential and logarithmic function. So, what will we be dealing here with? Okay, so first, let's start with function y equals e to the power of x. Look, we already discussed general properties of exponential functions, and actually there is not much more that we need to add over here. Because look, of course, the exact shape will be slightly different of the function. The general curvature will remain the same. Look, if x is equal to 0, we got a 1, and then this function looks like this. And basically, this is it. We already drawn the function. But look, we haven't used it in examples before because it's very inconvenient. Because, for example, if x is 1, y is e. If x is 2, y is 2e squared. And there's not much more we can do with this because e is not a very pleasant number to actually use. But the good thing is we know how much is it, so we can use it as e. And of course, please remember that of course if x is negative 1, y is 1 over e. And the logic of everything here stays the same. The curvature is almost identical as in the case with 2, but there are some properties mostly that you will see when we will start calculating derivatives extensively. They're very pleasant, and those are the properties we will not find in case of any other base. And look, now that we have natural exponential function, because this is how we call it, we can also start wondering about a logarithm with base e out of x, which we will simply call natural logarithm of x or ln x. And again, the curvature is more or less the same as in the case of base 2. So the function looks like that. Here we have 1, here we have x, here we have y, right? And what do we, again, it is rather complex to use actual examples, but for example, if we have e here, how much do we have here? To which power do I need to take e in order to obtain e? Well, the power of 1. The same if I would have here 1 over e, it would be negative 1. And of course, e squared, there would be 2. Okay, knowing this, maybe we can already notice some connection between natural exponential function and natural logarithm. Of course, this property is transcendent to other cases, but those cases are not that important, so we will focus only on these two. And look, we clearly see that there is some connection, because look, this function never appears in those two orders, in this region. It never takes negative values on y. On the other hand, this function never appears over here. It is undefined for negative values of x. Then we see that this function is growing faster and faster. This function is growing slower and slower. So where's the connection? Actually, the connection can be established directly by very small manipulation of the function. Look, if I have a function y equals e to the power of x, I can logarithmize both sides. And what will I get? ln y equals ln e to the power of x. But we know from one of the properties of logarithms that this x, being the exponent, I can move in front of the logarithm. And how much is ln e? So which power I need to take e in order to get e? Well, 1. So this is 1. And what we obtain is x equals ln y. And if I would switch the names of the variable, I would get logarithmic function. Now, exactly the same line of reasoning can be used if we start with natural logarithm. If I have y equals ln x, I can say anti-log. Anti-log means that basically I use both of these sides as powers, exponents for e. So we've got e to the power of y equals e to the power ln x. Okay, let's leave it the way it is here, and now think to which power I need to take e in order to get x. Well, I don't know this power. There is some power, but if I would take, remember, this is telling us to which power I need to take e in order to get x. So the result of it should be a power that will transform e into x, which means that we are here. So we've got that x is equal e to the power of y, which again, if I'm going to change the notation over here, I'm going to end up a natural exponential function. As you can see, this result one more time testifies to the strong connection between those two functions. And now this connection associated with the properties of these transformations actually should lead us to what is the nature of this connection. So, if I have here coordinate space, here I have x, here I have y, and I'm drawing e to the power of x and ln x, both in one graph. Let's notice some things. Here is 1, here is 1. Here, those two functions are very far apart. They are getting closer and closer to each other. At this point, they are extremely close. Then they are getting further and further away. If you think about it, if I would say a 45-degree line going through the origin, what would I get? A mirror, the axis of symmetry. As it turns out, those two functions are reciprocals of one another. So, they are mirror reflections with respect to 45 degrees line, and we can obtain the other function simply by solving for x or for y, solving for x, and then rechanging the notation. And basically, this is the connection we've got between those two functions. Okay, well look, now we've discussed logarithms, we've discussed E in very much detail, we've discussed exponential functions, and natural exponential functions and natural logarithms. But look, this class is called dynamic economic analysis. And in economics, we do not always use as much as can be used in terms of mathematics. During the first initial video, I also told you that what we will be doing in this class is dynamics. Dynamics means we need to introduce time. And look, now, every time when we will be using an argument, we will not call it x, we will call it t. And of course, t, which stands for time, has this property that it cannot be negative. Well, we can't expect, we could imagine that if we take a point of time as a point of reference, like when you have with BC and AD, before Christ and the Dominion. So we've got a situation where we arbitrarily take some point as the 0 point on a time continuum, and we divided it into 2 points. But as it will be with our economic applications, which will be more practical than this, you can simply assume that we start at 0 and then the time moves forward. We cannot change the past. Okay, and look, this actually reduces our interest only to positive, to non-negative argument, because it's 0. And look, we will be using very often general form of the function we just discussed, and this form is y equals a e to the power r t. Now, as we remember from before, so if we multiply exponential function by something, this will change the point at which exponential function cuts through, so intersects with y-axis. But look, in our case, there's no such point. This point is actually the beginning. Look, now we have time here, and how would we write this here? Look, if t is 0, this is 1, right? Which means that this is what we've got at the beginning. As you will see, most likely this is some amount of money we've got, and we will see what will happen to it over time. And actually, this is exactly why we use e, because look, then this value will be growing, assuming of course that r is a positive number. And r is a positive number. Now, if r is a positive number, we will observe exponential growth of this function. What is more, we will have, we can say that r is growth rate. Oh, let's call it nicely rate of growth. Again, this r will decide about the curvature, but we will discuss it in very much detail in the future. Now, all I want to do with you is one special variety of this function. What minus over here. Now, remember that in situations like this will be the same as y equals a to the power ERT, assuming that r is still positive. So look what is happening. Here we are dividing our initial amount of money, a, by some bigger and bigger number because this expression grows. And as a result, we have a function that looks like this. In this case, we call it rate of decay. Okay, in the next video, we will tackle derivatives. Thank you for your attention.